So here's another one of those torque problems that at first won't look like a torque problem. It's a ladder leaning against a wall on a floor. It's 10 meters long. And what they want you to find out is the coefficient, the minimum coefficient of friction for this ladder, between the ladder and the floor. The ladder weighs 100 newtons, so we'll put the force in the middle of the ladder. Of course, it's going to point straight down because that's what weight forces do. They point straight down, 100 newtons, and we want to find the mu minimum. You can't find that mu minimum unless you do a total force analysis, and it all begins by noting that the sum of the torques on this ladder equal zero because it's not rotating, and the sum of the forces equals zero because it has no acceleration in the horizontal or vertical direction. So let's figure out all the forces on this ladder. There's the wall, F wall, we'll call it FW. There's the floor, which is also the normal force for the friction, so we can call it F floor. I'd rather call it the normal force. There is the friction force that it prevents the ladder from sliding. We'll write a little F, and I think we've covered it all. So in order to get that coefficient of friction, looks like I'm going to need the normal force, of course, and the because friction equals the coefficient of friction that we want to find, times the normal force is the floor's force on the ladder. So I'm going to need to find both the friction and the normal force in order to find the coefficient of friction. Now, right away I realized that the sum of the forces equal in the x direction equals zero. So what does that mean? The force of the wall must equal the, pointing to the left, must equal the friction, the only force pointing to the right. So if I could find F wall, I could find friction. And I also know the sum of the forces in the y direction, they equal zero. So the down force is equal to the up. The down force is 100 newtons. It's the weight force of the ladder. And the up force is the normal, which is nice because now all I need is the friction force because I right now have the normal force. So remember I said it probably doesn't look like a torque problem to you, but it could be. We could do it as a torque problem. What do I want to find? I'm going to find the friction force. And I know that the friction force equals F wall, so I'd really like to find F wall. So I'll place my axis of rotation down here so I can eliminate the friction force, and I'll have this torque, the 100 Newton, and this torque. So let's do the sum of the torques because they must equal zero. I have two torques, the weight force and the wall's torque. Those two torques equal zero. So F wall times sine of this angle here. Now that angle's got to be 53 degrees because you've got that two parallel lines cut by a transversal. I'm just going to call it 53 instead of 53.13 if you don't mind. So that's the force, the moment arm. Distance to the pivot is 10 meters. We were told the ladder is 10 meters. So that torque equals this torque, 100 newtons down. What is that angle here? What angle does the force make with the normal? We've got a triangle here. See the triangle? We're already told this is 53, the base of the angle that the ladder makes with the floor. So if that's 53, this has got to be equal. Okay, let's get rid of that. This has to equal 37 degrees because 53 plus 37 is 90. So sine of the complement, 37 degrees, that's the force. And the moment arm is 5 meters because the ladder is 10. And then I solve for FW with a little, why do I want FW? Because if I get FW, I can get friction. So FW, let me look at my work here. FW is 75 newtons. Okay. And so let's see, do we have it? We have everything we need. So the friction, FW equals friction, so the friction must equal 75 newtons because the left force is equal to the right. Mu is the unknown, and the normal we already found up here. That is, but I have a mistake here. Hold on. Because this is not, when you do the math, you don't get 75. You get, that was I had done it before and I got it wrong. So that's actually, you get 37, excuse me. So when you solve this equation, you get 37.7 newtons. So now we can use the equation friction, which we found as, so that's FW, but it also equals the friction. Remember up here? So friction equals mu times normal. 37.7 newtons equals mu times 100 newtons. How do we get that? Because the up forces equal the down forces. Right over where, I can't find it. What do we do that? Actually, it's right here. Found it. So the 100 newton equals the normal. Divide both sides by 100 and you get 0.377 or 0.38 as the coefficient of friction. Let's do the next one. You've got another ladder, but in this case, there's actually you're told that there's a person on the ladder right here, and he's 800 newtons. So there's a down force of his weight force. This is a frictionless wall. Oh, I forgot to talk about that. They said this was a frictionless wall too. You've got the ladder, and its weight acts as if it's placed in the middle, 200 newton. Yep, ladder. And of course, you're going to have a normal force from the floor, just like before. And you're also going to have the wall's force on we'll call it FW. And there's no friction there, remember? And now I think we've got all the forces. We're also told that this ladder is 10 meters. It's good to put in the picture. And what do we want to find? That angle there, theta minimum. So we've got let's start with our first set of tools from Newton. Sum of the forces in the y direction equals 0. Let's see what emerges. So the down force is equal to the up. So what's the down? You've got 800 and 200. The down is 1,000. Hello. So the up force is the only up force is the normal. So you've got the normal force. And then we do again sum of the forces in the x direction equals 0. Left force is equal to right. So as I look at my picture, there's you know what? I realized I left another force out. There's a friction force down here. So I thought I had all the forces, but I missed one right here. Friction. I realized that when the F wall is the left, there must be a right, and that's the friction. We know neither of those two, so that's all we can do. Now I could do a torque problem. Sum of the torques on this ladder equals 0. So I'm going to place the pivot at the bottom, simply because there are two unknowns in the bottom, and I can remove two unknowns by placing the pivot at the bottom. They apply no torques. So you've got two torques going this way. The sum of the torques, though, equals 0. You've got two torques. The person on the ladder exerts an 800 Newton force. Sine of, well, check this out, actually. Are you ready? A little bit of trigonometry. Do you remember that the sine of 30 equals the cosine of 60? Or the sine of 20 equals the cosine of 70? Just take the complement. That's just how it works. So I'm going to take advantage of that concept. And I want to do 800 times the sine of this angle. However, I wasn't given that angle, but I know it's the complement of the bottom, so I can use cosine of the angle that I'm given. That's the force. The moment arm is 10 meters from the pivot, and that's the torque. And there's another torque over here. The 200 Newton ladder. Once again, cosine of that angle times 5 meters, and those two torques equal the one torque at the top, which is the FW. Now, this is also 53. Oops, my bad. It's not 53. Think about the other problem. This is theta, the theta we're given. So FW sine theta times the moment arm, 10 meters. That is the only torque in that direction. So that's terrific because, okay, so let's clean this up. Let's get all the cosines together. So we get 9,000, this is 8,000 cosine theta. This is 1,000 cosine theta. So it's 9,000 cosine of that theta equals FW times the sine, that theta times the moment arm of 10 meters. It's getting a little crowded here. So it comes down to this. And then, let's see where we go over here. So we can clean this up a little more. Divide both sides by 10. It's 900 cosine theta equals FW sine theta. Now we're told, I didn't put this in the picture, but I should have, this coefficient of friction is 0.675. So now, what's so good is I know the normal, and I know the coefficient of friction. So friction equals mu times normal. So I can actually find the friction. So 0.675, we were given that, times the normal, which we found up here. Remember, that's 1,000. So the friction is 675, yep, newtons. Now, but we also know, it's quite complicated, isn't it? The friction equals the FW. So I can go to this equation over here and replace FW. So 900 cosine theta equals 675 newtons times sine theta. Now we're going to employ our old trick of dividing both sides by cosine theta, divided by cosine theta. That leaves us, and we get 900 newtons equals 675 tan theta. Divide both sides by 675, and I can get my angle. So tan theta equals 900 divided by 675. Take the inverse tan, you're going to get 53 degrees. Is that angle that will, let's see, the angle, the minimum angle is what we want, theta min. Theta min. So that there was a lot to that. How about we'll do a little overview. If I'm going to find theta min, what do I do? First thing you always do is find all the forces. I initially left out the friction, remember that? So there certainly is a friction that prevents this ladder from sliding. There's an upward force from the floor. There's a force from the wall. There's a force from this person on top of the ladder, that's down. There's the weight of the ladder. Then I did the old first quarter stuff. Sum of the force in a y direction equals 0. There are two down forces from the ladder and the person. That equals the up force, the normal from the floor, the only up force, so I had that. Then I did the sum of the forces in the x direction, just the force analysis. The wall's force must equal the friction because there's no x movement of the ladder. And then I do the torque problem with my pivot at the bottom, the two torques of the ladder's weight and the weight of the person. And one of the other tricks that you should know is this over here. The sine of 30 equals the cosine of 60. The sine of 20 equals the cosine of 70. That's how that's why I use cosine for this angle here. Instead of sine of the angle, it's the cosine. It's the cosine of the angle because that's the complement. And I did the same thing with the 800 Newton person. So you might want to look at that one again. Slow it down, pause it. That's it.